now it's the turn of Jonas Ries. It comes from EMBA at Heidelberg. So he is the author of the software SMAP. And I should also thank him because he participated to the challenge and he participated for all modalities we will see later. Thank you.
Thank you. Yeah, while we wait for this for the screen. So I'm a group leader at EML in Heidelberg, and my group is developing and applying advanced super resolution microscopy methods. And the software we are using in my lab, basically I wrote it, and it's called SMAP, a super resolution microscopy analysis platform. There, it's almost there. Yes, great. Slideshow. Okay. So it's really great that we are meeting here to compare our software and that so many people participated. But I think it also kind of points into the direction of maybe a problem in the field. And that is that so many groups are developing their own super resolution software from scratch instead of using existing and really good software packages. And this continuous reinvention of the wheel kind of, it wastes some resources which might be better used to implement new ideas, new fitting algorithms, and so on. So the last time I rewrote our software, I had this in mind, and I tried to write it in a way that it's as modular as possible, but also as easily extendable as possible. Yeah, for our biological collaborators mainly, and also now for us, I tried to have an easy to use and customizable user interface, and of course I want to have all the great functionality around in the internet and in the community. So here you see an overview about the different analysis steps of typical super resolution software. You go from camera images to the list of localizations, which then you can render as super resolution images, and then you have to analyze those, or you directly analyze the localizations. And all these steps, of course, depend on many parameters which are usually provided by the user. So in SMAP, in our software, all these steps are encoded in what we call modules or plugins. These modules are actually quite easy to write. You take a template, put in a few lines where you define the user parameters, which are then rendered in the user interface later, and then you implement your specific functionality without much worrying about the rest of the software, and finally copy it into the plugin directory. Although most modules are really independent from each other, they can talk to each other using a global parameter structure. This we use, for instance, to synchronize fields of the user interface. Also, every module saves its parameters, so afterwards you can always know what you did to your super resolution data, which analysis steps you performed. So modules can then be connected into what I call workflows. It's just really a list of connected modules which run on the dataset one after the other. And we use those workflows especially for the fitting part. This is a typical fitting workflow we use. And the reason why we split up the whole algorithms in so many individual plugins is because that makes it very easy to exchange some part of the functionality without worrying about the rest. So if one of you comes up with a better way of, let's say, doing a background subtraction before the peak finding, you implement it as a plugin, and then you just exchange the module in the workflow and don't have to implement a user interface or a reader for the camera frames. So at some point, if you have so many plugins and want to define the user parameters, it gets a mess. You have to go through this list of maybe 20 plugins. You don't want to do this. So that's why we map the user controls, the input, onto one page in the overall user interface. So it's easier to configure. And these workflows can be easily assembled just with a mouse click. In my group, we mostly use the GPU-based maximum likelihood fitter from the Keith Littke group. But in the software also implemented, or actually I just took the radial symmetry in 2D and 3D, and the high density Falcon fitter. 3D we usually use, or we usually do with astigmatism, but in the software you can also use biplane or double helix. Something which we really like to do, and which is quite nice, is that we can fit already during the acquisition, also render and analyze our data during the fitting. And with this real online analysis, we can immediately see if a data set is good, or if we want to go to the next region of interest or the next sample. For the rendering, I wanted to have some kind of Google Map-like feeling to explore the data, to move around, zoom in, zoom out. So I implemented a fast renderer. Again, there are different plugins, different functionalities, how to render the data, and you can write your own. but we most use a Gaussian renderer, where every localization is rendered as a Gaussian with a width proportional to the localization precision. Not the same, but proportional. Then we have different layers, and each of these layers can be rendered individually, and in the end, the layers are just overlaid on top of each other. And this allows us to display different data sets, different channels, or just, as done here, overlay a diffraction-limited image with the super resolution data. And we can basically filter on any property of the localizations. Because it's really quite easy to write plugins, we already have quite a few. And at some point it gets messy, it gets difficult to find the functionality you're using most or you want to use. And this is why we have a configurable user interface where you put the plugins you use on a daily basis at well-defined positions, and all the others which you usually don't use, you can still access from the menu. Also, it's possible to define optional parameters together with default values, which can then be hidden in the user interface, and this makes it easier to use the software, especially for our biologists. Now, I briefly want to show you two plugins we use a lot. One is a real-time 3D viewer, or 3D renderer with several render options. It can do these stereoscopic images with the cyan red glasses or with these Google Cardboard-like viewers for your cell phone. It works, but honestly, for me, it gives me mostly a headache. Another quite nice plugin which we really use a lot is the so-called ROI manager, where it can automatically or manually segment your data set into regions of interest. You can annotate them, also automatically or manually sort them, filter them, and then pass all these regions through an analysis pipeline. And finally, do a global analysis on all your data. And if you come to my talk tomorrow, then actually most of what I'm showing there was analyzed using this ROI manager. So to summarize, our software is quite modular and I think quite easily extendable. It has a hopefully easy and at least customizable user interface and a lot of functionality. At some point, if I find time, I might publish it as open source. Until then, just write me an email if you want to use it. So it's based on MATLAB. On one hand, this has an advantage because many people know how to program MATLAB and maybe are more likely to provide own code for this. On the other hand, of course, not all groups have MATLAB, and then one has to use the compiled version. Then not everything is MATLAB. Some parts are written in CUDA, C++, and Java. So in principle, we can also use plugins written in other languages and other platforms, and then we have to interface to them. And we interface actually quite closely with Micromanager and ImageJ. So now I think I still have a minute, and since this is a 3D competition and we spoke a lot of simulated data, I wanted to show you some real data, which we image just using the standard astigmatism approach and the DNA paint, just to show you that in practice at least our software can do 3D fitting and drift correction. So these are of course microtubules, and if we now use our 3D viewer to reconstruct the side view like this, you see that all the microtubules appear as this hollow cylinders. This is clear, the fluorophores cannot enter the microtubules themselves, so in the center you always have this black line, but you need a really good resolution to really see this. But if you have this resolution, then you can really think of using super resolution microscopy to segment microtubules in cells, even at these really dense regions. You just have to follow these black lines through the cell. So in the end, I want to thank all the people who struggled with all the bugs and with the daily updates almost, and gave me still constructive feedback, and you for listening.
Is there any question? We have time for one or two questions. Yes?
Yes. So, how does the support of other algorithms work? Do the developers have to adapt their interface into your MATLAB codes, or how do you see it happening?
So I would imagine that you have your algorithms there, and then at some point you read the documentation once it's there, and you know how to interface it, because it's not so many different data formats there you can pass on. I think for the fitting, you either go from camera images to list of localizations, or you do something with localizations and so on. So it's quite straightforward to understand how to interface it. And then it's probably just a small wrapper, a few lines to put the right data into your algorithm and take the right data out of it again and pass to the next module.
Thank you.